on the dais. We will be initiating a talk on the progenote, the last common ancestor of the extant life. His achievements and contributions, some of them are as follows. Dr. Sarkar is the lone living academic grandson of Professor P.C. Ray, practicing science. He is the former head chemistry department of IIT Kanpur and is presently Honorary Professor Emeritus at the Chemistry Department of BSU. His research of over 45 years in the diversified fields on the biomimetism of the metalloproteins originated from the chemical evolution of the extant life from archaeal hyperthermophiles to latest mesophiles, including human. He has also many other research activities, one of which is nanocarbon technology, in which he is a prominent figure. He has guided about 40 PhD students. He has delivered several invited lectures in various institutions and served as a visiting professor, and he is a fellow in the several organizations both in India and abroad. He writes popular scientific articles in English and Bengali dailies, and he also writes short stories, mainly satire in Bengali. Now I request Swami Sarvapurnananji Maharaj, our Secretary Maharaj. I am very sorry, my apologies. Swami Sarvapurnananji Maharaj. Swami Supurnananji Maharaj. My apologies, Swamiji. To honor our guest speaker, Dr. Sarkar, and hand over the life of Swami Vivekananda by his Eastern and Western disciples, Volume 1 and 2, and a book titled Science and Religion, published by Advaita Ashram as a token of appreciation and thanks for sharing his valuable knowledge and time. We thank Swamiji for being personally present to encourage our efforts. Before we start today's proceedings, here are some announcements. Initiation of discussions would be over by about 7:15, followed by participation by the audience by way of questions and comments either in Bengali or in English. The next lecture in this series will be on 30th August 2013 by Professor Nandalal Pariya on biodiversity and conservation, an overview. I invite Dr. Sabyasachi Sarkar to kindly initiate discussions.
Shraddheya Maharaj, Shudhi John, যাকে আমি বাংলায় বলছি, friends. The topic today that I have chosen is definitely a difficult in all respect to understand, but nevertheless, it is probably the simplest possible thing that happened in this earth long ago. The question comes that the progenote, the word comes from progeny, that is the first initial life, and I try to cover that several people that they try to make it understand how the life was created on this earth. And in this respect, that what I wanted to cover the last common ancestor of all extant life. Now, to start with that, okay, no problem. To start with that we have to take into account the evolutionary history of life on Earth that traces some of the living and fossil organisms that since the world, like the planet, first originated something like 4.6 billion years ago. The question comes that actually that Earth was created 4.6 billion years ago, and then with this type of record, the life appeared on its surface within 1 billion years. So just when Earth was created, Earth has to wait for another roughly 1 billion years, and then the first form of life evolved on this Earth. The question comes that the similarities between all present organisms, that indicate the presence of a common ancestor from which all known species have diverged through the process of evolution. So I am going to call back that real sense the Adams, that the first, not restricted to human but to life. Now, precisely that the 0.8 billion years, that's 800 million years journey of the elements. The elements were created from after Big Bang and supernova explosion, that all the elements that what we understand from chemistry and physics, and life is nothing but, matter is nothing but the association of those elements. So once the elements are formed, from there the life that what we call prana, that was created 0.8 billion years ago. Now it is important to note that this life of the prana in Greek, that is called pneuma, and that means air, to breathe. The question comes, 3.8 billion years ago, there is no air to breathe. What do you mean by air? That is no oxygen. So there will be definitely a life which started without using oxygen for their survival. Now in Krishna Upanishad, Pran, that is known, born from Atma, is Deva or God. And what it says, I alone dividing myself fivefold, support this body and keep it. So that's the Upanishad, that what we understand from life, that how it's. Yeah. Now, what we understand from the modern day perspective? The modern day perspective states something like that. Understanding what life is one process that consists in representation of nature. Philosophers of Vedic order investigated the founding principle, the 5 elements that permitted them to understand the world. But here, modern scientific understanding of the world culminates with the convolution of 4 elements: matter, energy, space and time. And it is summarized by the remarkably short formula EMC square. There is the 5th element to define no privileged position in the universe, and we refer to Heisenberg uncertainty principle. So these are the 5th. These are the 5 here also. But the question comes here, there is this strange absence of a novel element, and that is information. And that information is something that is missing, and that one has to try to see. Now, several people, they believe that is life came from outside, from asteroid, or it is originated in Earth. So these are some of the fundamental questions that people ask, and the people who believe that life came from outside, there are plenty. Actually, that is the first philosopher, is a pre-Socratic Greek philosopher, Anaxagoras. He proposed this, the Greek word, panspermia, and that seed. So the seeding is created from outside, that he said. And he has the followers like these celebrities: Virgilius, Helmholtz, Arrhenius, Fred Hoyle, Vikram Ranasinghe, including Stephen Hawking. All they believe that the seed came from asteroid from outside, and that came and then it started growing in this earth. That was the situation there. Well, so panspermia talks about biology. Hardy microbes hitchhiked to Earth on comets, and all known life today descended from them. But how microbes are originated? Let it be there, let it be somewhere in the universe. But wherever they are created, they must have been created. But by which means? How it is originated? These are built up by elements. These are the fundamental elements by which the combination of these elements they create life. So whether on Earth or if it is carried by comet, it must have been created somewhere. How it is created, there is no answer by this type of model that how. They simply say it came from there. So if we talk about elements, then definitely the supernova, as we know that explosions inject carbon, oxygen, silicon and other heavy elements to the interstellar space. Without supernova, the fiery death of the massive star, then there would be no carbon or oxygen or other elements that to make life possible. So we owe to supernova, we owe to Big Bang, so that the elements are created and they unite in some process by which the life is formed. Now, some of the astrophysicists was trying to understand that even how these interstellar dust, they combine to produce some of the molecules, and what they started to see that in the center of our Milky Way galaxy, some 26,000 light years from Earth, here the cloud called Sagittarius B2N, where one could analyze and one can get this type of some of the peculiar molecules that they are created there in the interstellar dust. So people are trying to find out that what could be those things and whether they have any building spirit, any block by which we can try to narrate that they by some means get together and they contribute in the formation of life. And this interstellar cloud is 99% gas and 1% gas. Now based on that, a physicist, astronomer, Carl Sagan said, we are all star stuff, and obviously, because we are created by elements, so we belong to stars, so we are all star. In that way. So he said we are all star stuff. All elements in our bodies come from stars that burst and seeded the galaxy. And this is physics, definitely, this is physics. But how this assemble to create life? That is a fundamental question, and people are trying to evade that fundamental question all the time. So, element used to create life are from Big Bang and from supernova explosion, that's we know, that is physics. Life possibly arrived from outside or evolved on Earth, that is the sperm theory, that is biology. How life is originated from non-living elements? That's right. They don't speak anything on that. So, if we try to see, physics vows us with the origin of the universe and biology delves into the evolution of species being the two fundamental mysteries of existence. But then, how did life arise from non-life? Now, here the chemistry is the nature, that is the teaching, that is the place, that we will find the answer to the biggest of the big question, that how life evolved. So I'll be referring to something related to that to make it some belief that this is the way, this is the process by which the life originated. Now before that, try to find out that some people, they try to understand different things, the development of modern day science, and there are some names like Socrates, Plato, Aristotle. They, via Arab world, the European learned. What they learned? To investigate. And but what the investigation means? By examining what everyone else had said about the matter, making several observations, and finally deriving either general or probable principle on the matter from both A and B. Now, the scientific revolution started from Copernicus, Leonardo da Vinci. They started addressing, making the universe visible. Kepler and Galileo, they started making the universe move. Bacon and Newton making the universe move mechanically. So it's a stage of events that what Bacon borrowed alchemy from our world to discover gunpowder and professed, and that's very important. Knowledge should not be derived from books, but from experience itself. Experiment comes from the word experience. Controlled experience is experimental science. So it is something like that one has to experience, one has to do the experiment to have experience. And based on that, if you have a controlled experience, and that is nothing but experimental science. Now what I plead for this, because since the discovery of fire, that is the experiments that people they have done. Many great scientific discoveries are made. Chemistry is based on experiments and directly descended from alchemy. So it is based on experimental science. And based on that, the people try to find out where one can find life and how it is. So this chemistry, the way one looks, there are diverse ways that people are trying to see this earth. Now, if we try to talk about origin of species, it started, the Darwin started with this language, this sentence. God first blew life into one or a few forms, and then evolution took over. Darwin is very, very skeptic, very, very afraid, because he saw what happened to Galileo. I mean, one cannot avoid those type of church, the dictate of church, that you say something, very much something unique. Knowing in his heart that what is actually he wanted to talk, 11 years later, he said, in a letter to his botanist friend, Joseph D. Hooker, suggested that life may have had a chemical origin. So that was in his heart, but what he wrote in the original species, that God created. So fine. You can say God created, then the matter ends there. So you need not do anything. Now, is it possible to extrapolate from modern biochemistry back to the origin of life? So today the biochemistry, you know that what is life. If we try to if we try to go back, slowly, can we get the back? Actually, how life started? Is there any way by which we can do that? So these are some of the questions. But before that, try to understand the stairway time history of life. This is the part that I am referring to. This is the Precambrian era, this is the Paleozoic era, this is the Mesozoic, and this is the Cenozoic. And here is human. The question comes that this is the hidden era, it is something 4.6 billion years ago. Is the Archean 3.8, and this is Proterozoic 2.5. Here. I'm trying to talk about the obscure life here, and that must be of mineral origin that we would see, and this is called, that we refer to as chemical Darwinism. Normally we talk about, there is a green marker, but the evolution of oxygen came, there is 570 million years ago, and this oxygen is toxic to this obscure life. And this is the biological Darwinism. It goes in this way, and it's a different stages. We know the Mesozoic era, Himalaya formation, Jurassic Park, all those things. This happens here. That is the rise and fall of dinosaurs, all this, and then it is Cenozoic the human. So this part probably we know, but this part is completely dark, and life started from here. So we want to, today I want to address this part, how the first progenote probably appeared. That's the Darwin's dilemma. The Darwin's dilemma is that when all of a sudden the explosion of animals 570 million years ago, so with a huge oxygen level, one can get this fossilized some sort of creature at that time that appears. So this is a fossil, and what evolution is a theory, is guided by natural law, has to be explanatory by reference to natural law, testable against the empirical world, conclusions are tentative, testable and falsifiable. Now the problem is that here, that this is the tribolites that I have shown. It is something in the primitive type of life form, that fossil they have started at that time, and what they said, they print, if the tribolites fossil, and at that time if one can find the fossil of mammals, then the Darwin's theory would be completely rejected, but it's not. We don't see this type of thing. It is the latter stage, by dating, by knowing how old what is, and people can make it, this is the older than mammal. So evolutionist theory, and that way they said, yes, this part slowly evolved. But the question comes that we are not encouraged by that what happened to 570 million years ago. We are interested to know what happened the earlier time, the first form. Now, that is something that one can say, is it elementary? So, try to recreate the past. So, I'm trying to now understand that how we can recreate the past. So, what are the things that we can have by which we can build? Obviously, this is based on experiments. As I said, the chemistry is based on experiment, and we have to take into account all those experimental observations put together and try to find out whether we can have some notion about the progenote or the first extant life. Now, the chemical evolution of cellular life, the question comes that how did the earth metamorphose from the lifeless planet to the world teeming with living organisms? How could complex life have originated from non-living chemical elements? How the very first microscopic life on primitive earth could have evolved as a result of a series of chemical reactions. So if you believe that there are a series of chemical reactions, we have a number of how these are actually progressed, so that from the non-living, a lot of matter, all of a sudden one can find that there is a life. So how that can be described, or whether this event can be focused by some means. Now, before that, one has to understand a couple of things. The restriction. The second law of thermodynamics proves evolution is impossible. But then, fortunately, the Earth is not a closed system, but an open dissipative system, and continues with evolution so long it gets energy from the sun. So it's not closed. So that does not violate second law of thermodynamics, fortunately. And obviously, it is directly related with the sun. We know. So long sun exists, we exist. So now the question comes, that some of the people that started thinking that can we do something chemically to get the fundamental building block of life, that some of those species which we know they are essential for life. So it's operating, the Russian biochemist, 1924, he first thought there must be some material origin of life. And with this idea, that I summarize some of the things that people are trying to make it, the Miller and Urey showed that for the gases of prebiotic atmosphere, something like these are nothing, there is no free oxygen. To electric discharge was sufficient to produce at least 11 of the 12 amino acids making up the proteins of life. Oro showed the creation of nucleobase adenine from hydrocyanic acid. Straker showed that aldehyde, ammonia and hydrogen cyanide can create amino acids. Now what I mean, that all these small molecules, they were available in this type of primitive environment, and they started to show by different type of chemical reaction that there is a possibility that one can get some of these important elements which are very much essential for life. So later on, a biogenic route to the nucleic acid bases, the ribose-like sugars and the polyphosphate, the basic constituents of RNA and DNA are made. So all these were made in test tube, piecemeal by n number of different people. But even then, if someone put all them together and shake it and bake it, one cannot get life. That's you know. So there are ways and means by which chemically we can get all the fundamentals, ingredients, what we know, understand that they are essential for a life. But even then, if we put all together, you cannot see the expression of a living object. So there must be something more that one has to address. So the question comes, the creation of the effective home. There should be a home where this thing can start, and this is nothing but the protocell. The other ingredients are available, but there should be a protocell. Now, the cell is important. Cell is very much important to understand that what is cell. Now we talk about all these are very common. It's a textbook that one knows that the DNA, RNA, proteins, and these are the three, and people say this is life. So I can take DNA, I can take RNA, I can put all the protein in a pot, go home, next day I should expect the life would originate. No, it does not take place. That's not that simple. The question comes that the DNA can create RNA, RNA can create DNA, and then both require to make protein. Sometimes RNA itself can create protein without the help of DNA. So this part is general and this part is special. Nevertheless, so we are not bothering which came first, but modern science knows it is the RNA which comes first and then DNA. But that is not important here. But at least one should try to talk a little bit about DNA, RNA. Otherwise, with life, there will be some people who are very much fond of DNA, RNA. They will be talking that no, probably the talk is useless. Anyway, so the basic structural unit required for protein synthesis is something. These are some of the fundamental molecules. Don't go by the clumsiness of this, because these are some of the fundamental molecules. They can be individually synthesized in test tube. So it's not a great deal. And then it is something that they have this type of phosphate chain, phos1, 2, 3 phosphate chain, and here is one sugar, and the base could be anything like that. Now this chain is there, and there will be some staircase that we can show a little bit here. Yeah, it's something like that. That a phosphate, then phosphate, the sugar is there, and in this way they can go. If this chain is depicting like this, then these are in between. So we need not go for this part very much, because that's not that important at this stage. So one have this type of this helicity where all those actually the phosphate backbone is there, phosphate, 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 and then dangling this nucleic basis is here there, and they can have this type of coil and they can unite. So it is double strand, it is a single strand, that's all we know. But we are not referring to any complicated here. We simply think that to make the assembly of this we require a Herculean task. How one can do that in the primitive form. Now there are ways and means that I wanted to show that how these can be created. Now, Hardy, J.V.S. Hardy, obviously. He was in India, he became Indian. He said, Irradiant sea under prebiotic atmosphere, I mean just I have taken from Google, some of the rough sea wanted to see, that is the Archean Sea. And here, it can be divided in two parts, that it has the bottom part and it is the surface part. So what happened to surface? The small nucleic base and other elements, they were here broken or, and what is sea? That's in the night, the sea surface temperature cools and these single strand RNA DNA acts as template in the formation of complementary strand. They wanted to be coming close and close and close. At B, or you can say that the B, the late afternoon, it heats up and beyond the denaturing temperature. What I mean, DNA RNA normally it has been shown that at higher temperature, the coiling, they are completely get ruptured. Ultraviolet radiation comes and they just get chopped. They get part, they get be separated. But in the night time, when the ocean gets cool, they once more with a permutation combination, they can make several different type of combination. And so for days and months and years and years and years, it's a process, a continuous process that every time all were in the daytime, high UV irradiation, so whatever strand is formed, that was broken, chopped off. And in the evening when it gets cool, then they wanted to stay together and wanted to make something new, and every new experiment, and then try to use it for something. If it is not matching, the next morning as the sunrise, once more it is getting cleaved, and then they try to have a readjustment. So it is an ongoing process. Unfortunately, for any human being, we can do this experiment, say for example, at the most 40 years, 50 years, 60 years. Very fortunate for us, it got 800 million years to do this experiment. So every day it tried to do this thing, and then it can have assorted several this type of situation that was floating on the surface of the sea, and beneath, that is on the down. Now I will talk about the chemical evolution, how that these are available. So let us try to rephrase it once more. That is a Big Bang, and then I'll be talking about the mineral origin of life, the progenote, the ancestor of all extant life. This is the part, and follow through chemical Darwinism, biological Darwinism, and these are some of the things that we know nowadays. Okay, so here only. So once more, there is the phylogenetic tree type of how these things, the chemical evolution, and some of the things that one can make these small molecules, and the origin of life somewhere here, the common ancestor, and then you have a branching of all those different type of species. So this is later on. So we are still restricting to this part. Now here, I am referring to cell. For matter, the smallest unit is known as the atom or molecule. From physics and chemistry, we know the smallest thing is an atom, and we cannot divide an atom. That is the smallest. But what would be smallest thing for a living object? The smallest object of a living object is a cell. So it is the cell, the smallest unit of life, contains a semi-permeable membrane to separate it from the surrounding and still maintaining selective contact with the external world, just to have the second law of thermodynamics. Inside the cytoplasm, inside that whatever the milieu is there, is chemical molecules including some macromolecules like RNA, DNA and protein. So our question, how a complete cell is formed? A protocell, the ancestor of all cells. I can make it that every day we see a cell, a single cell, but roughly speaking, it's not that defined. Some people can object, but I can say that is a cell. A chicken egg is a cell. So one can see that a hard calcium carbonate coating, and beneath it there is a semi-permeable membrane. So that's important. So that membrane is very much important, and that takes care of this interior ingredient of a cell that stays back. And that's important. Even today, there's none who could repair a cell. A living cell, if you try to open it, that's the end of the story. You cannot repair it. So a cell is the essential smallest ingredient of living object, and it is housed by some of those molecules including DNA, RNA. But then nobody talks about how this membrane, which is separating from the surrounding, and it can house all these things, that how that is made up of. So let us try to see how this is made up of. So the question comes, it's a progenote, and this is a bacterial lineage, archaea and eukarya. The oldest is archaea. That's the first. It came, and it is a lineage that goes to bacteria and eukarya, where we belong. So we are close to archaea. Now also we should try to understand the first law of thermodynamics. This organism will have to obtain energy from an outside source, change the form of the energy and use it to build or maintain it. The energy cannot be created or destroyed. So that means a cell should have contact with outside. There should be passage by which it can get some foodstuff or something so that it can transform that to other form. So there should be some association. That one cannot violate. Though, for most of the things, it restricts to go inside, which are not good. It debar, it prevents that, it does not allow that it should go inside. So cell is most important. So for a cell, what are the important things? Maintenance of a cytoplasmic volume separated from the bulk medium. That's important. Its ability to perform some catalytic conversion, energy. Reproduction with the passage of information to ensure that offspring is relatively similar to the parent. So these are some of the objectives of a cell. So that's the reason cell can divide and cell can go. And once cell is a living cell, that means that's life. So a theory of the origin of life must explain how cell compartments are made, how are constructed the first replicating molecules, correspondence rule between memory and manipulation. A primitive metabolism provides a solution. Now what could be that? Now how one can get? Now Earth tried to do this type of chemistry, this type of experiments. So Earth's experiment is with solar energy on the surface to utilize to create larger molecules like RNA, DNA, which I already covered, that with all piecemeal, small molecules are created inside, and then on the surface, the DNA, RNA, but then the geothermal energy buried under sea to create smaller molecules, you need to create larger molecules and to create semi-permeable membrane of the protocell. So the lower part of the earth, that has created something more under the sea, and where the semi-permeable membrane of the protocell it creates, and also it creates small molecules which floats up, and they combine to provide you the macromolecules that we refer to DNA, RNA. So in the gradient of the primordial sea, the top and the ground, both they are involved to create that life. Slow transfer of geothermically driven chemical reaction under solar energy was with necessary adaptation. That's the latter stage that we want to see how that takes place. So based on that, let us try to find out some of the evidence, the fossil evidence. The oldest well-preserved fossils on Earth have been discovered in 3.6 billion years old, just roughly when the life started. Rock in Western Australia. The fossilized microbes were found alongside the mineral pyrite and iron sulfide, nicknamed fool's gold, which is a byproduct of their consumption of sulfur compounds. So that one has to have a deductive knowledge that they could get some fossils of the living object, microbes, but they are along with iron sulfide. Now what that speaks? One has to read those things, and what the scientists, they read it in this way. Light prefers to use lighter isotopes, as the chemical bonds then takes less energy to split. As pyrites contain high amounts of sulfur isotope 32, sulfur can have 34 also. So the distribution of 32 and 34, that is by nature, that is conserved when the Earth was created, when the supernova explosion took place. Now slowly, if one can see the distribution is something preferentially all 32 and very less amount of 34, then one can believe that these are slowly adapted and these are slowly utilized by this microbe, so accumulated preferentially only 32, because the bond energy to cleave or to utilize using 32, you require less. And obviously for any object, one has to prefer where less energy to be utilized. So that is the reason that the sulfur or sulfide, the iron sulfide is formed, that is evolved in this process. So the fossils were encased in mineral silica and found in black colored sandstone, from which is now the oldest record of life is shoreline or beach like setting. Silica is very strong, we know, which has helped these microfossils survive so many years without being squashed or without damage. So silica prevented any damage to that, and we can see this thing. So this much we could observe, that a primitive life, the first type where it utilized iron sulfide, that is the message that we could get, iron sulfide. And that's probably important aspect here to talk about. Now, this is important that I was talking about the chemical Darwinism, which is the bottom case. Biological Darwinism we know, all we know. The survival of a protocell carrying all information to communicate. How a protocell can survive. A small isolated domain separated by a membrane from the surrounding, which may qualify to call a primitive cell. The membrane could be made up of iron sulfide, just we said, we saw there, and precipitated the formation of new bubble that we want to see. There could be proton gradient, and that could be diphosphate as a ATP, and we explaining this, what is the meaning of that. And reaction takes place in the gradual incorporation, you are sulfide ingredient. Okay, what do you mean that? But before that, it's important that these are the two named reactions, Fischer-Tropsch and Haber-Bosch processes in chemistry. Now, these are very important reactions, and they require high pressure, high temperature, and some metal, oxide or sulfide as catalyst. Nothing more. So very fundamental molecules, if those things are there, and if a high pressure, high temperature, then all those small molecules, initial startup molecules, can combine to create some larger molecules of interest. So this Fischer-Tropsch can provide a lot. However, we know that if you have nitrogen and ammonia and hydrogen, you can create ammonia. So with a high pressure, and so these two reactions are very important to build some of the primitive molecules. Now here I stated some jargon which is probably not understandable. Let me try to explain. A cell where one can have that there is a protomotive force. What do you mean by protomotive force? That cell try to create, synthesize certain things. The most important is ATP. The ATP is the energy currency, adenosine triphosphate. It is something as we use money to buy something, to utilize something. For biology, the energy currency is ATP. So ATP is utilized and it is changed to some other form. Once more, it has to be resynthesized. Once more, it has to be resynthesized. I can make a statement here that, say for example, in my body I have inorganic phosphate or ADP is to the tune of say 200 milligram or 1 gram. Per day, I make ATP and consume it energy to once more ADP and then once more ADP, once more, and to create that I eat a lot of food. And total, if we sum up that, how much ATP created, that is 25 kilos. So the normal food that what we take, the food has the ability to create 25 kilos of ATP. But that is too much. So what the little one we are having, every time we are creating ATP, consuming it, once more ATP. Now to create that thing, it demands some situation where we know acidity, that's called proton. So the membrane, across the membrane, there should be a difference in acidity, inside and outside. There should be a difference so that then the proton can flow. Because as for example, if there is a water height different, then water would be from the higher height, it can flow to the lower height. So here also the proton, if the membrane, across the membrane, there is some proton gradient, the difference in acidity, so there is a movement of proton to neutralize. So there is a proton gradient that is important for synthesis of ATP. That is a fundamental issue for a surviving cell. That is one important, and then another important thing is that this ATP synthesized is adenosine triphosphate. Already I stated the adenosine is created by this very simple way, hydrocyanic acid. Hydrocyanic acid is deadly poisonous. This potassium cyanide, something like that. It can be polymerized to create a very important molecule, biomolecule, adenosine. And triphosphate is nothing but phosphate. That's normal phosphate, diphosphate, triphosphate. So these two things to be incorporated across the cell. In the primitive case, adenosine may not be there, but even diphosphate has got phosphate-phosphate bond that can be utilized. Now here, the gradual incorporation of near sulfiding in the iron sulfide, say for example a membrane is created by iron sulfide, and then the organic thiol which can be created by Fischer-Tropsch process can be incorporated here, and some other important molecules can form. The picture would be something apparent and can be understood in a follow-up couple of slides. So, a cartoon of this type of thing, one need not read everything, but what I wanted to, this is the head and ocean, this is the depth. On the surface, which I already depicted, that we floating of DNA, RNA, all sorts of things. But on the ocean floor, it is something, the descending sea water, here, one should try to understand. Here the temperature is hot, here temperature is cool. Why the temperature is hot? The temperature is hot, there are some vents where from these gases are coming, oozing out. This is a vent. This is a vent, and it has been enlarged here. So here you can have all sorts of metal and hydrogen, carbon dioxide, iron, phosphate, all these things. And here, try to understand 4.6 kilometer of hydrostatic pressure. So the pressure is there. There's no problem. The pressure is there. And as it's a molten lava coming out, oozing out from here, the temperature is high. At the near vicinity, temperature is very high. Of course, water is there, so water would be here, it would be very cold, it would be 20 degrees, but near where the 3000 degree molten lava is coming out, in the near vicinity, the temperature would be very high. High pressure, high temperature, both are there, and then Fischer-Tropsch type of reaction can take place because it's full of all these type of metals are there, and some of these small molecules are there, these molecules. What do you mean? That hydrogen is there, carbon dioxide there, methane is there, sulfur is there, one can get the corresponding thiol and different other type of molecules, a larger molecule, a little bit larger molecule, which would be essential for building block to create even macromolecules, those will be required. So this is the kitchen where small molecules are synthesized at the bottom of the sea. After top, the small molecules wanted to have the UV radiation, and with the day, night, in this way, the permutation conversion is taking place to get the suitable molecule, and this is happening, and this is the high thermal vents. I have some more picture for that. So it is a hidden volcanic era. How Earth looks like was like ocean of liquid rock, boiling sulfur, impact craters everywhere, volcanoes blasted up all over the place, and the rain of rocks and asteroids from space never ended. The air was hot, thick, steamy, full of dust and cloud. It was completely anoxic, no free oxygen, and was made of nothing but carbon dioxide, water vapor with traces of nitrogen and smelly sulfur compound. In any life formed on Earth during this era, it is difficult to visualize. Can we find isolated place on this modern Earth keeping the environment similar to 3.8 million years ago? Can we find something very much similar to today? The minimum requirements for that is it should be no free oxygen, hot, and mostly minerals with no organic matter. So these are the minimum criteria. Whether you can have some space like that even today, fortunately we do have. This is a black smoker. That is beneath the Earth's surface where the volcanic eruption is taking place. And then this is all metal sulfide, black sulfide, the iron sulfide. The gigantic plates from the Earth's crust is just like a tsunami type of things happening. Every time it's there somehow, and Earth plates are moving apart, creating cracks in the ocean floor. Seawater seeps into the opening and is eaten by the magma that lies beneath the Earth's crust region. It's mostly iron and sulfide, which combine to form ferrous sulfide. The compound gives the smoker its black color, and local water temperatures raise up to 400 degrees centigrade. That's what I was referring to. It's a 400 degree, 3 kilometer down water, so hydrostatic pressure is enough, and so we can think of from chemistry point of view, any molecule you try to synthesize can be synthesized here. But it is something very important here that I marked. Very high concentration of tungsten. Here. And the interesting point is there. Today you can find some life form here, and that precisely people can get. Some living object is available here at this hostile environment, and they are very, very primitive in nature. Try to understand, it's a ferrous sulfide, no sun, there is no oxygen available, and so hot, and some small microbes are available there, and they don't like this present atmosphere. If you bring them up, they die. They don't like this atmosphere, but they survive only here. And they are very much close to Archean origin, primitive. And here, they try to have tungsten, because here is a lot of tungsten there, and they have a lot of tungsten inside body in different form of proteins. There's something important to understand. We do not have any tungsten inside our body, even including bacteria, other microbes, including human being. But we do have not tungsten, but molybdenum. And this is the younger brother of tungsten. So it is something that one can make it, that just a 400 relay race. A qualification of tungsten is something like that. It is a very stable, sturdy. It can do its reaction at high temperature, a molybdenum cannot do. And then it started running when the temperature is hot, very hostile environment. When the earth gets cooled and the temperature all sets to proper action, then it just hand over its baton to its younger brother, that is molybdenum. And it took it. The environment is exactly the same, and then it is distributed not only to bacteria, fungus, everything, including human. That we do have some of these enzymes in our liver. Now I wanted to show you something, that environment which I recently visited Bokreshwar, and that is near to our home, near Shibpur. That you know that there is a hot spring, and this is beneath that, this type of a vent is there, which is all the time coming out the gas, and then some of the heliums are coming out, and there are the people they have taken care of so that the helium can be, one can take care of the helium. So here it's all the time that the water is boiling and something is oozing out. Our Bokreshwar, here, one can go there and can have a look. So that's what I wanted to mean, that some of these organisms, all they are very primitive and they stay there, and they have tungsten, iron, sulfur, all this. They love to be here. These are the things, some of these. It's highly unreactive tungsten that is involved in the first pyroelement redox reaction at elevated temperature near hydrothermal vent. So there are n number of species that people they have isolated, so they stay very near, and they love to stay at very high temperature. So one can model this, that we have also modeled this in the lab, some of these things with the tungsten, and what the reaction they do